can start. Welcome to the Transportation Speaker Series. Today it's our pleasure to welcome Professor Hamdar from George Washington University in Washington, D.C. Professor Hamdar is a graduate, he received his undergraduate degree from American University of Beirut, master's degree from University of Maryland, and his PhD from Northwestern University. And we actually share the same advisor. So
different graduation dates.
That's the different locations. As he moved, so did he. Professor Hamdar is an expert in driver behavior modeling, in traffic safety, and I guess the dynamics of movement of people. So, and he also has he chairs the CAV, the Connected and Automated Vehicle Subcommittee at TRB, and is a member of the Traffic Flow Theory and of the Emergency Evacuation Committees at TRB. He is also a recipient of the Career Award, and we are very pleased to have him here. And the floor is with Professor Hamdar.
Thank you. Thank you, Dr. Soni, for the welcome. Thank you all for being here. So let me just say what I do work on in general. So I work mostly on safety and collision formation. And that's one of the reasons I joined the George Washington University. So before I joined, the George Washington University hosted the National Crash Analysis Center, where they did outdoor impact tests. So that's actually one of these tests. In this case, they are actually crashing a Tesla. And it worked well. It doesn't look good, but it worked well. And practically, the idea was the National Crash Analysis Center mostly work on finite element modeling and the behavior of the car when there's a collision. I would be there to be able to recreate such system using human-driver interactions. So that's the main idea. And that was the idea of the Career Award per se. And practically, we adopted two techniques. The first one is a data-driven technique in order to analyze different available data resources when you have collisions. The other one is more behavioral modeling technique. And practically, we did that through building a microscopic model, car following lane changing, and simulate that and collect data in order to recreate collisions. So, as a motivation, well, the motivation is clear in terms of collision formation. So these are some of the numbers from NHTSA, National Highway Traffic Safety Administration. And practically, what you see all the time, even though in terms of numbers, the corresponding collision may be stabilized, but in terms of rates, they are not. So fatality and injury rates and the collision rates are increasing on US soils. And even though it's stabilizing from time to time, the technologies that are being introduced are not actually allowing us to analyze that for a long period of time. So practically, the fatalities are increasing from 2015 to 2016. They are increasing now, but also not because of collision due to freeways, but mostly due to pedestrians. And I heard you have scooters collisions here. So also because of that. The second also reasoning is most of our car following and lane changing model, actually not most, all of our car following and lane changing models are collision free. They are built in a collision free environment. And practically, if you think about from a behavioral perspective, most of the collision that you see on the roads, especially on the freeways or uninterrupted flow conditions, like angle collision, rear end collision, and side swipe collision, you can see them here, they can be explained by the behavior that led up to that collision. And practically, we would like to understand such behaviors and the corresponding risk-taking attitudes of drivers. Now, you say collisions, well, we say collision and we say congestion at the same time. So, of course, as the congestion or the travel or the vehicle miles travel increase, as the congestion will increase. So these are some numbers from INRIX from 2016 all the way to 2018. And we can see that the cost of congestion and the corresponding average time spent by each driver during congestion and the cost per driver are increasing. And if you think about Atlanta, where you are not on the top 10 list, I'm sorry about that, you are not the most congested city, we are way above you. But what's interesting here, you can take a look about the increase in congestion from last year until this year, practically 10% increase. So these are some of the data just illustrating that congestion patterns will be changing and most probably will be increasing despite the technologies being adopted. It's a simple equation of supply and demand. And with congestion, you have collisions. And with collisions, you have congestion. So practically, if you think about some of the reasons behind congestion, it is, again, by the Federal Highway Administration and even in Washington, D.C. So this is from the Federal Highway Report of 2017, where you have different categories of reasons for congestion. Traffic influencing event like traffic incidents, road zone and weather. Traffic demand, so if you have special event or commute related traffic patterns. And physical highway features like traffic control devices and even infrastructure. All of them contribute to congestion. And if you look at Washington, D.C., well, practically you have high demand, weather, and incidents are a major reason for congestion, and you expect to see that in urban environments and economic environments. So, with all of that, what would be my objective? So, we have two objectives. The first one, O1 over here, it's practically to build some data-driven techniques in order to predict collision formation. That's number one, and to understand the corresponding traffic flow patterns. So with that, the modeling side, I can tell you from now, we didn't finish it yet. We hope to have collaboration to do that. But from the data side and the data mining, well, I think we did a good job, and we will show some of the results on that regard. On the other hand, from a modeling behavior perspective, I think we did a good job in the modeling side, and we were able to calibrate the model and produce collision involvement rates, but still we would like to get more data because data is a very high commodity if you talk about behavior. So, how I'm doing that? For the first objective, O1 over here, what we are doing, we will analyze the fundamental diagram patterns with collision formation. We will look also at AI techniques, neural network technique, in order to detect collision formation. From the formulation side, the behavioral side, that's objective 2, I'll present a little bit the formulation and the calibration and simulation results, and I will tell you what we are doing right now at GW to collect data on that side. So let's start. From the fundamental diagram aspect, we didn't want just to plot collision numbers or fatalities depending on where you are in the fundamental diagram region. What we want to do is to capture collision involvement rates. So what we did a quiet data mining effort, and we introduced this again, this factor, the collision involvement rate, CIR, that will let you number of collisions per million vehicle miles traveled. And it all depends on two velocities, the upstream and downstream velocities, so we mine that. And at the end, you get a rate. So we did that actually at the beginning for NG-SIM data. And we wanted to look at the collisions, and we linked the collisions from, again, 3 years with the car trans detector data because you have a detector upstream and downstream of this region. And we linked that to the HSIS, the highway safety data repositories. And we extracted the collision involvement rates and we placed them on the fundamental diagram. And that's what we got. So again, if you remember, we are looking at collision involvement rate not just based on collision, but per type. So we looked at collision involvement rate for rear-end collisions and collision involvement rate for angle and size-wide collision. One that's mostly explained by car following behavior, the other one mostly explained by lane changing behavior. And practically what you see, so it's a three-dimensional shape here. The flow and the density, so that's your standard fundamental diagram. And on the z-axis over here, you have the collision involvement rate. And this is particularly for rear-end, RE over here. So we did some clustering analysis, so that's fine. Collision involvement rates and collision points can be clustered in parallel to the different congestion regimes. So you have the free flow, the transient, and the congestion regimes. But don't look only at the numbers, look at the collision involvement rate. So it is represented by the z-axis again. So if you look at rear-end collision, mostly they are located in a band going at relatively low flow value. Again, this is for the entire flow, so if you divide it by the number of lanes, you can see it's very low. And they range all the way from low density to high density. So they are not only on the congested side, but they are always from the free flow all the way to the congested side. And they are high all across the board. And this is very different than the side swipe and angle collision. So most of them are not at the high density area. Most of them are located over here when you are returning from the congested regime back to the, again, free flow regime. So that's fine, but practically the only thing this will provide us, depending on where you are on the flow density diagram, it will give you a warning about the collision involvement rate that you expect. So that's fine, that's helpful, but we want to have more, especially from a behavioral perspective. So we said, okay, and this is Jorge's work, he's not here, but how about on the macroscopic fundamental diagram level? Can we look at collisions and look at that from a macro or network level perspective? So why we want to do that? Well, we want to predict future traffic and possibly apply different assignment techniques or routing techniques due to collision formation. But for that, we need a large network and real data. So there has been some work, again, looking at the causes of disturbances on the macroscopic phenomenon diagram, either because of the junction positions or because of incidents, but most of this work are based on simulation, not real data. So practically, the main limitation is, of course, network heterogeneity when you want to construct a macroscopic phenomenon diagram and study collisions, and the incident characteristics. We need really a lot of data here. So where did we go to? Unfortunately, in the US, you don't have that much. So we went to South Korea, and we collected the entire detector data and the entire collision data from 2011 until 2013. We are mining more this year. And we looked at the entire collision. So I'm not sure if you see, these are detectors. It looks like a straight line, these are detectors, okay? So they have actually a high frequency and high coverage of detectors in the freeway network operated by Korea Expressway Corporation. So we looked at all these collisions, okay? And we started redrawing the network there by dealing with two things. Number one, the discontinuous links. So we had to redraw some of the links. So you can see these are the detectors and they are all over the board. And also, we looked at heterogeneous link because of the coverage. And practically, after a lot of statistics, we focus on practically 3 days. The first 3 types of days. The first type is related to the days with the most collisions. So these are the ones. There are 2 days with the most precipitation. And they have there also I think it's a holiday, it's called Chuseok holiday, it's like Thanksgiving here, where you have very high demand. And we redrew the entire MFD of the network, the Korea Expressway Freeway Network. And we focus on 2 parts. Why? Because the full network, as you see, we don't see that congestion formation. So it didn't go to the capacity reach. But for the Seoul network, if you look at around Seoul, it is a little bit more congested, but not still fully congested because, again, look at the density, it's very low. So all of this is because of the network heterogeneity. But still, we were able to get that curvature, and we have 3 patterns. The first pattern is associated with the high demand. So practically, that's what we see. So actually, it's a simple hysteresis loop over here, or here for the full network. And practically, the increase of the hysteresis will increase as you go further to the right side. If you have collisions, however, that's not what you see at all. Practically, you don't see capacity reach, so you have big chunks of the network that are unused. But what's interesting is the hysteresis loop will increase as the capacity reduction increase. So practically, we want to try to model that. And the final thing with the bad weather, we always consistently see an inverse H shape of the MFD. So practically, you go this way, you go down, then you go this way, then you go this way. Okay? So these are some patterns that are very interesting. And we still, again, in the data side, I think we analyzed quite some data, but in terms of the modeling side, we still don't know how they look from a behavioral perspective. Now, we did that further with looking at subsections of the network. So these are, for example, data also from Korea. And practically, we looked at 2 types of collisions. The first one is a total road closure. The second one is partial road closure. And I'm not sure if you remember the beginnings of the slide. So this is the location of the collision. This is where the star is. And here, this is the location of the collision. You don't see it a lot, but it's over here. What do you think? This one, is it a side swipe or rear end collision? Based on the data from our earlier study. So is it relatively high volume or small volume? Anyone? Compared to this one. So is it located at relatively high volume or low volume? So this is for rear end. This is for side swap. Okay? So if you go back to the corresponding slide over here. So this one, what do you think? Is side swap or rear end? So if you remember, when you have rear end collision, there is a band at the low flow value. So if you look at it this way, this is actually a real collision. And it's transferable, of course, because it's partial link closure. For this one over here, it occurred at this transition point at relatively high voltage. And this region is a high collision probability region for side swap and collision. So actually this is a side swap, and that's why you have a total road closure. So there are some patterns there. But also what you notice, as you integrate, so this is for one link, if you integrate the 10 downstream and upstream links over here, and same thing over here, the impact of the collision will be actually, again, diluted, and you will not be able to notice anything. So the problem became for us is we didn't actually were able to reach, so we are doing the method of cuts now, but we didn't reach a technique to be able to model such behavior, that's uncertain behavior, from a traffic flow perspective. So what did we do? We went and we looked at an artificial intelligence technique where you don't need to understand what's going on. You just use it to predict collision formation, okay? And that's the approach we use after we tried the first approach. So this technique is applied, and we applied that in Virginia. Why in Virginia? Because we were able to receive the data at high resolution, true, but also we were able to receive the speed distribution, not only the flow, speed, and density. We were able to receive the speed distribution patterns when you have different collision formation. So there are two types of detectors there in Virginia. So you have the AVC, the automatic vehicle classification system, so that's actually on the ground. And you have also the wavetronics, so this is what you see mostly these days. And both of them, of course, are good in terms of detecting the speed distribution. The only difference is this one can tell you if it's a heavy vehicle versus non-heavy vehicle. This one can't. Okay? But all of them can give me the speed distribution. So what did we do? We mined all the data. So these dots, you can see them. This is Washington, D.C. These are detected data for Virginia. And in addition to getting the counts, for each vehicle passing through each lane, what we were able to get the speed bin. So in which speed bin it is located. Now technically you should have that in South Korea also, but they didn't provide us such data. So we had to use this technique over here, but not in South Korea. So we mined the 2014 to the 2016 collisions, all geo-encoded, and we had all the interval data in terms of speed bins, and we used that, again, a recurrent neural network technique with a long short-term memory module, okay? And why we did that, so practically what did we do? We used the speed distribution, the current speed distribution and the previous two speed distributions to predict the future speed distribution. That's number one. At the same time, we used the long-term memory model because we went back 1 week before, the same time, the same hour, okay, the same day, and we use this also to predict the future speed distribution. So at every time step, what we are doing, we are predicting the future speed distribution, and we are comparing the predicted one with the actual one, and based on that, we can see if there's an incident or not. Okay, so that's the general technique that we used, and practically we did that for different detectors. So these are some of the detectors. So this is for all freeways. We also incorporated 3. So these last 3, these are arterials. Still, you don't have that much around the detector. You didn't have signals, but still arterials, so it has its own characteristic. And what did we do? We set our objective function using the RLN technique with LSTM to detect at least 80% of the collisions. That's number one. But also to be able to have as few false positives as possible. In other words, we don't want to have false warning systems. So we did that, and these are the results. So these are for different detectors. So the collision detector rate across the board, it goes between 80 all the way to 90%, if you notice. So we detect 80 to 90% of the collisions. Of course, for arterials, these are the 3. Notice we didn't detect 80%, we detect 70 and above percent of the collisions. And at the same time, what we found, we have many incidents. So collision actually occupied only around 5 to 10% of the incidents occurring. What are the incidents? You have either work zones, you have weather issues, you have police cars or security personnel, you have, again, dead animals. So all of these are incidents. But we were able to detect all of them. But what we noticed, collisions are not the main occupying factor when defining an incident, and that was a major thing when we talked to VDOT, Virginia Department of Transportation. So just to give you some ideas how this looks like. So at every time step, so this is the horizontal line, we are predicting the next time step, and these are the speed distributions. So of course, the lighter the color, the higher the distribution, meaning, sorry, the higher the percentage of vehicles passing through that speed distribution. So if you notice, we are predicting, and of course, while we are predicting to be over here in this region, what happened is there was a discontinuity. What does that mean? It's an incident, a collision formation, or an incident formation. And the idea is to play with the error threshold to minimize, we trained the model, to minimize false positives, at the same time to detect at least 80% of the collisions. So for example, if we lower the error threshold, we'll detect much more incidents over here, okay? If we increase it, we'll detect less. So in this case, it was only one incident, and that's fine. In this case over here, it was 2 incidents, so that's why the threshold is over here. And so you can see 1 incident over here and 1 incident over here. And finally, in this case, if we increase the threshold, we will detect how many incidents? 2. But in reality, it's how many? It's 1. So that's why you need to be careful with the interplay between incidents and collisions and your detection rate. And this is something that wasn't captured by other researchers working on collisions in general. And that's one of the reasons, by the way, it's very hard to capture collision formation, because of that uncertainty involved and other types of incidents involved. So we took this and we did some platforms. So this platform we did for Korea University and KAC, where you will have the 3D flow density and time relationship, and we automatically tell you where the collision is, and based on that, it will appear on the corresponding screen. And we did the same thing for Virginia. So this is some platform. So practically what happens is you have different detectors depending on the trained data that we have. And whenever you have a collision, you will see it here automatically appear. So in this case, you can see what's going on. It's a collision formation. And based on the AI technique, we actually have more results. Now, of course, I will talk a little bit more about these videos because that's another thing we are doing, also for safety applications. So this is what I have to say in terms of the first 2 objectives associated with data-driven work, okay, and collision prediction. Now, the second part, it's on the other side of the spectrum. So this is more at the data-driven side and macroscopic side. The other side is microscopic and behavioral side. And practically, this was my original work when I started working at GW. And practically, the idea is existing car following and lane changing model are built to be safe, correct? And practically, why is that? Because they are not stochastic. There is no uncertainty. Most of them are deterministic. And if they are uncertain, for example, the BTV-VSIM model, what you have these error thresholds where you have different behaviors, but they are built in order to, again and again, avoid collisions. That's why you have an emergency braking paradigm, so that you won't get involved in collision because it's not equipped to do that. So instead of using these models, what we did, we developed a model based on prospect theory. So prospect theory, for those who work on decision-making theories, so practically you take an objective utility, okay, an objective gain or loss, and translate to a subjective gain and loss. So if you say you are working on gambling, if you gain $100, if you are rich, you will perceive it as peanuts. If you are poor, you will perceive it as a significant amount. So there is this kind of interplay between objective and subjective gains and losses. And we said the same may apply for what? For driver behavior. It's a decision-making process. So from the acceleration side, your gain can be approximated by the gain in speed. So the gain in speed that is standardized over time as well is simply the acceleration, correct? So practically, your objective utility might be approximated by the acceleration. Your subjective utility will be translating this objective utility by this function, okay? So of course, the logic behind choosing this function, it has been explained in multiple publications of ours, but practically, it will allow you to be either risk averse or risk taker. So practically this one, it's risk averse because drivers in general are risk averse in nature. That's why you decelerate more than what you need, and that's why you have shockwave gradation and amplification. And Also because it represents the non-linearity at the extreme. So the more you are at the extremes in the gains and losses, the less you will perceive them with respect to your relative point. So that's the main idea behind that. And if you formulate your system like that, then you can incorporate also a collision probability that you can estimate actually, even if you are not involved in a collision. That was the main thing. And at the end, if you have utilities, well, your entire acceleration function is not deterministic anymore. It's stochastic. So once it's stochastic, and once you have a built-in environment for risk-taking behavior, then we can recreate trajectories and possibly we can create errors. So that's for the car following. For the lane changing, we use hazard-based duration, where you have also stochasticity and patience and snowballing effect, among others. So you can estimate the duration of time where you decide to follow a given car. Once you decide to leave that episode or leave that duration, it's what? It's a lane change. So we estimated that using this technique. And we, of course, check the mobile safety paradigm using our acceleration function. And in addition to that, because I want to model collision formation, I have to model the lateral trajectories. So we explicitly model these trajectories. And we explicitly model the vehicle dynamics limitation. And we incorporate all of that at the end of the day by capturing the entire proximity of the cars. So we are not modeling like existing car forming and nature models. We are capturing the extremities. We are capturing the location of the center of gravity and the mass of the car in order to have also a post-collision movement. So some basic results, so you can see we are modeling the lane changing, the lateral one. So it's not just an insert in the adjacent lane. And another aspect, so this is before collision, they impact here and then they move, the cars move afterward in different directions. And all of this is incorporated in our model that we calibrated. So that's something where you have a model that's calibrated, but with what? With collision formation. So that was a really challenge for us. So we want to have trajectories with collisions. So we were able to get some of them using the NCAC crash film library, but also we had to model our own simulator, have our own simulator that will allow collisions, because existing simulators, once you collide, there's nothing. That's it, you restart. Now we had to incorporate this in a simulator to see how we will behave also. So we calibrated the model, and then we simulated that. So the good thing, it can recreate all the fundamental diagram regimes without any problem. So this is, for example, recreating the NGSIM data, and you have the shockwaves propagating backward. Okay? So we did that, and we simulate that for a long time. Okay? So we simulate that. What can we do when we simulate that? We can simulate the input and the output speed, meaning the speed bends. We can simulate the behavior based on the calibrated parameters, and we can recreate collisions. So I can do that. I can go back to my original study. I can create collision involvement rates. I can create speed bends, and I can see if the two matches together. So we are linking the microscopic side with the macro aggregate side. So that's what we did in this project. And we collected a lot of data. For example, these are some data where you have, again, Korea data, and we have link 1, link 2, the length, the upstream density, the flow, and speed, the downstream density, flow, and speed, and the corresponding collision involvement rates. So if I take something like that, and I have a model that can recreate collision involvement rates, what can I do? I can simulate it and see what will that get me. And not only I simulated that without any warning, what I did is also, we simulated that with different warning systems. So in other words, you will see the impact of each warning system on the collision involvement rate. So now we are explicitly modeling collisions again. That's the new part. Okay? And once you do that, so we did some behavioral analysis. So these are the warning systems that we tested. So baseline no warning, auditory warning only. So practically it's simply a sound. Okay, so practically, and as you go down the list, you have more information to process, correct? So from a behavioral perspective, using, of course, the standards for safety warnings, what we wanted to see, if you provide more information, like you do for routing purposes or traffic assignment purposes, if you provide more information, is it good or bad, okay, for drivers? And we did that, And we looked at, again, information from 0 to 5, 5 where you have the most warning, and 2 where you simply give a non-informative, so the driver will not know what to do, correct? But at the same time, symbolic. So there's a warning, it's a symbol, it doesn't require a lot of information. And the last one, of course, is alphanumeric, but it's informative, it's telling the driver what to do. So once you do that, we collected a lot of human factor data. I won't go over the details, but some interesting fact. Notice that when you talk about age impact in conjunction with the warning type, reaction time is changing all across the world. Okay? So age, not gender, age was a major part. Okay? That's number one. Number two, the biggest difference were between warning 2 and warning 5. And remember, warning 2 is the minimum, warning 5 is the maximum level of information. But how did that occur? We did the experiment, so this is based on the Career Award. We did the experiment for 2 types of young drivers, high school and teen drivers, okay, and young drivers from the age of 20 to 25. 20 to 25, they reacted the best when you provided the most of information. The teenage drivers, they reacted the worst when you give them such information. Okay? So practically, giving more information to some strata of the drivers actually will have a negative impact. Now we expect that in other research related to routing among other attitude-based research, but for collisions, we weren't able to do that before until we have such modeling approaches. Okay? And in addition to that, so these are some parameters of the car following and lane changing models that we developed. So this is the weight for collision. So it's increasing significantly across the age, depending on the warning system. And this is the anticipation time and this is the reaction time. But how you look at risk-taking behavior is related to WC. That's the weight for the collision, a subjective weight. Okay? So at the end, this is the important side. So these are Korea data. These are our data with no warning. Okay? This is, if you create only auditory, notice it's performing relatively well because these are the collision involvement rates. They are reduced. If you look at scenario 2, what happened? It became a little bit worse, or because of statistical significance and to be prudent, at least it didn't improve that much, okay, for this strata of society. And of course, 5, it improved significantly more. So actually, this is problematic when you provide warning, okay, and when you simulate, but the collision involvement rate will increase, and the warning will not work accordingly. So these are some things that we were able to do. Now, so this was a 5-year project, and we started from the modeling to the data collection to the mining to the human factor research simulation until we get this result. Now, what we are doing, we want more data, of course. So if you remember, this is the part where data is appreciated. So we built an autonomous car, okay? And now we are just collecting data for validation purposes to match the auditory system, the warning system, the base one only, the auditory, that's the only one we are allowed to do in human subject research, but with no, of course, with no near incident scenario, because also we are not allowed to do that. Once we do that, we can validate the simulated data with this data, okay? That's number one. So, number two, what we are doing, we are translating these environments into a virtual environment. Okay, so we built our Unity 3D system to collect, so in other words, if I want to recreate NGSIM data in the simulator with the entire system, with my behavior, I can do that. So we did that, and practically at this stage we were successful, so next semester we'll collect data on that. So this is the environment we have. So it's a multiplayer environment, it's a simulated environment, where we can have near incidents, pre-incident, post-incident behavior, and we can play with the different warning systems that we want in an interplayable system. And again, most of our focusing for this award on young drivers. So again, we tested different systems. So this is a 3-screen system, this is a curved screen system, and practically this is another system in Washington, D.C. because you can play with different systems in different regions. So we have multi-drivers, so just to illustrate. So these are 2 drivers interacting together. nice cars, but here these are autonomous systems. So also we can build the autonomous logic with which we want to drive the car. So in terms of future extension of this work, also focusing on safety. Remember, my focus is on safety. So we can do mobility things, but my focus is on safety. So we are also developing a CAV system. So this is a CAV car where you sit in the car, you don't do anything, unless what do? You overtake it. So we want to test disengagement with respect to collisions. And that's a major aspect. That's practically what you see when you talk about Tesla and all these investigations. It's actually the near incident disengagement event, how you will behave. So, unfortunately, well, we know that this exists for airline industry. They do that all the time. You have such simulators. In the auto industry, you don't have that because for some reason we are behind. So the good thing, we develop the system and we can compare the behavior of different people, either in autonomous versus non-autonomous versus autonomous. So the other thing is we work on, and hopefully we can collaborate in the future, is crowd behavior modeling. So that's another extension. So practically, remember, collisions in freeways, it's a big section, but you have a lot of collision with scooters. I think you have how many? 3, 4, 5 last semester here, correct? Also with pedestrians, it's a major thing. So we extended our model. We were able to extend the prospect theory model for a 2-dimensional scheme. So practically, we have a directional prospect theory utility where you can have your direction. So for example here, your maximum utility corresponds to this region going straight, and this is your destination. You can go left and right. So this will be like a potential field, and you move in a potential utility field instead of a potential force field. Okay? So we extended that, we were successful in doing that, and we were able to recreate bottleneck scenarios. So this is some data based on my collaboration with TU Delft. So this is what they did, this is what the observed data, this is what we simulated. So practically we were able to use prospect theory to model that. And again, why I'm interested in that? Because now I can even try to recreate collisions with pedestrians. So now we can see that, and we can see the interaction between them. And of course data. Of course it's harder to collect data with pedestrians, cyclists or scooters than when you talk about cars. But what we did for that, because data is high commodity, we were able to create our own logic. So now we can extract trajectory data with bicyclists, pedestrians, and we did that in a highly intermodal environment. So if we have such trajectories, and if we can calibrate the previous model, then what can we simulate? We can simulate collision, and we can analyze them even in a virtual environment like this that we built. So to conclude, what did we do? We analyzed collision formation in freeway environments, and we did that from a data-driven perspective and from a modeling perspective. And we were able to create some data collection tools to do that. And we were able to extend the behavioral model now to be applied for pedestrian decision-making process. That's what we did. Now, what we want to do further? More data. So every time I send a request and we get more collision and more detected data from Korea, from Virginia, or other locations. And we are improving our data collection tools. So the virtual environment now for pedestrians is a little bit, it's literally we need to wear a mask. So we are providing that, and we are simulating, we are implementing incident events. And of course, once you have these tools, we need more experimental human factor research and more calibration for the models in different aspects, not necessarily only for young drivers, but also for, again, elderly drivers or, again, different types of drivers depending on the type of community that you have. So, and then, again, thank you first and foremost for the opportunity. I want to thank all my collaborators, so from VDOL to, again, University of Juan Carlos in Madrid, Texas A&M, TU Delft, KAIS in Korea and Korea University, Federal Highway, who funded the work on the AI approach, and of course my students who work on the modeling part and the AI part, and hopefully in the future I can see also Joyotech over here. Questions? Yes, please.
Since you did focus your studies both in Korea and Virginia, I'm just wondering if you could kind of like observe any differences in driving behavior leading up to the crash, and how much of that is sort of detectable through your experiments and studies?
For the AI technique, we couldn't apply it in Korea because we don't have the speed distribution. KDC is very proprietary for that. But from just look at the patterns themselves. Okay? So in Korea, actually, it's much worse than here in terms of collision patterns, especially the side swipe collisions. Practically, the other thing that we noticed, we did some experimental setup using driving simulator data. They are more receptive to technology. So actually, they can handle technology better than us. In other words, what do I mean? If you provide them more information, they are better, especially young. Again, we are working with students mostly. Young drivers, they are better in handling technology and responding than our population here. Again, I said our population because I will not say for the entire US population of young drivers. It depends on the experimental setup. But this is an interesting pattern that we can build on. So, in general, they are more risk taker, but they are more prone to technology than here. So, if you think about it, then if you introduce autonomous systems, then the behavior will be very different there than here. That's something to keep in mind. So, for example, here, we expect, so next semester we'll do the experiment, we expect that we'll have much more disengagement events here with younger population for using the autonomous system. And unfortunately, like it is for pilots, if you take over the autopilot, you will tend to do more errors. And that's something that is related to the acceptance of the technology itself. And that's some research that you might be doing in that regard. Questions? How many of you were interested in studying collisions? Why no one studied? Very few people study collisions.
So, I'm wondering, have you looked into the current technology related to collision prediction, such as in Tesla's cars? I believe they also have their own technology, maybe neural network most probably, to predict collisions. So as far as we have seen here, you seem to build your own microscopic lane change models and carpooling models to try to capture the probability of collision.
Yes.
So we have seen you use the neural network for the macroscopic part. So have you tried to use the same technology to the microscopic models?
The micro?
Yeah.
No, because I'm not interested in that. The problem with the microscopic behavior, I want to understand the behavior. If you are looking at AI approaches, the AI approaches, again, it's a good approach to recreate behaviors, but you won't understand really what's going on. And that's one of the limitations of this technique, even when used by Tesla. So practically what I'm trying to do, as I showed you, the WC parameter, how can I reduce it? By how much I can reduce it, depending on the warning system. That will not be captured by AI technique. So AI technique may be good for prediction for systems that, or for behaviors or for patterns that already observed, or that you trained your model for. Otherwise, it will be unlikely. Maybe with some modification in the AI method, there are some research on that, predicting the unpredictable. But until now, they are not that successful, and because of that, you have Tesla accidents.
Yes.
So, from my perspective, AI technique is good for application, for quick applications, for real-time applications, but not to understand behavior. And that's why I didn't apply it for the microscopic side. For the macroscopic side, well, that's fine. For the microscopic side, it will be too late. One error is enough, and that's a problem for me.
Yeah, it's really cool when I see your microscopic models. The results are consistent with the previous part of the microscopic fundamental diagram. So, have you done research to evaluate which method is better when we trying to use the results to predict the impact of collisions? So I mean, if we try to predict the congestion or predict the impact of collisions on congestion, so which method should we go first? The macroscopic method or use the micro models?
For congestion in general, there have been a lot of work on using the macroscopic approach to detect collision and even to control traffic.
Yeah.
So they have been successful doing that, including Professor Laval, including Vehicular, including Vehicular. So they have been doing that for a while, and also it's been applied even for policy and energy consumption use. I think by Eric Gonzalez from the University of Massachusetts. For collision, no success yet. So I think it will be faster if we started both together, but I started with the microscopic earlier. So at this stage, I think that I'm more advanced from the modeling perspective on the microscopic side than the macroscopic side. But I think from the macroscopic side now, I think it wouldn't take us 5 years to do that. So I think in the future we might have success very soon with some collaborators. But it's very hard to model the traffic dynamics at the macro level with collision formation, because collision themselves are, again, they are not moving bottlenecks, so you don't have to estimate them like moving bottlenecks, but they are uncertain bottlenecks, and they are random, and you need to study first the corresponding creation of these collisions spatially, then temporally, both in a stochastic manner. And how to incorporate that in your macroscopic Hamdar diagram, and how to do that while capturing a pattern of formation at the macro level. I didn't have success yet, I was frank, but hopefully in the future it will be faster than my work that I started with microscopic approach. Make sense?
Are there any other questions? Dr. Pita had to go to class, so he asked me to wrap things up, but we still have some time for any other questions, or you can stay for a few minutes afterwards. If not, we'd like to thank Dr. Hamdar very much, and I really enjoyed it.